For more than 2 millennia, pieces of rock rich in magnetite were a source of profound curiosity. To early observers like Thales of Miletus, who credited the magnet with having a soul, the lodestone appeared to possess an invisible, animating power that could pull iron across a distance. Without a reliable way to maintain a heading away from the site of land, early human civilizations remained geographically restricted, unable to navigate the featureless reaches of the open ocean. This diagram shows a Chinese south pointer from the 1st century BC. By carving a lodestone into a spoon and allowing it to rotate freely on a polished baseplate, geomancers created a tool that reliably oriented itself with the Earth's magnetic field. That concept evolved into the dry-pivoted mariner's compass, which became the essential technology for the Age of Discovery. It gave navigators like Zhang He and Christopher Columbus the precision needed to map the landmasses and oceans of the planet for the first time. Simply by harnessing an invisible, unexplained phenomenon, humanity was able to expand its physical reach across the entire globe. In 1600, William Gilbert began stripping away the superstitions surrounding the lodestone by proving that the Earth itself is a giant magnet. He demonstrated that compasses don't align with the stars, but with the Earth's own magnetic poles. This allowed scientists like Edmund Halley to conduct the first magnetic surveys across the Atlantic. His charts of magnetic variation showed how the field varied by position, allowing trade fleets to correct their headings and plot safe routes across open water. While the scientific method provided a map of the Earth's magnetic behavior, it left the underlying cause of the force a mystery. For the next 2 centuries, global trade and exploration remained dependent on a planetary force that no one could yet explain. The relationship changed in 1820, when Hans Christian Orsted noticed a compass needle deflect when placed near a live electrical wire. That single observation established the formal link between electricity and magnetism. Michael Faraday expanded on this by developing the concept of the magnetic field. He demonstrated that a changing field could induce a flow of electricity, proving that mechanical movement could be converted directly into electrical energy. James Clerk Maxwell later translated these observations into mathematical equations. This theoretical framework gave engineers the precise tools needed to build the first practical electromagnetic machines. This is the Nobbe-Grams 1870 dynamo, an industrial-scale converter capable of turning mechanical rotation into a sustainable flow of electricity. By spinning this central toothed rotor within the surrounding magnetic coils, it creates a steady electrical current, the foundation of modern power generation. Using these principles, Nikola Tesla designed high-voltage alternating current systems. This made long-range power distribution efficient, allowing cities to replace gas lamps with local electric grids and safe domestic light. By the end of the 19th century, this second magnetic revolution had established the foundation for global communications and high-voltage power distribution, even though the internal mechanism of the magnet remained an unsolved puzzle. A massive scientific contradiction emerged in the early 1900s. According to classical physics, the electrical currents required to make iron magnetic are so intense that the metal should have melted entirely. Classical physics dictated that magnetism shouldn't exist at all. Resolving this forced a transition toward quantum mechanics in the 1920s to explain how matter behaves at the subatomic level. Scientists identified electron spin as the source. This intrinsic angular momentum generates a magnetic moment without the need for macroscopic currents, providing the first coherent explanation for why solid materials can be magnetic. Understanding spin allowed researchers to stop observing magnetism and start manipulating it. They focused on hysteresis, the way a material retains its magnetic state after an external field is removed. To master this, they used instruments like James Ewing's automatic curve tracer. This device allowed them to map exactly how different steel bars responded to magnetic excitation. Mapping these curves allowed metallurgists to move beyond simple iron. Over the following decades, they developed synthetic alloys and rare earth magnets with energy densities far greater than any naturally occurring stone. This shift from classical to quantum physics moved humanity beyond simple observation, enabling the precise engineering of synthetic magnetic materials for modern industrial tasks. By the 1950s, the first mainframe computers began using magnetic tape and bulky storage drives to preserve and process large amounts of digital information. The breakthrough came with Spintronics, controlling the spin of electrons within thin film layers just a few nanometers thick. This allowed magnetic storage to shrink exponentially, matching the speed and scale of modern semiconductor chips. Today, that engineering forms the backbone of the information society. Trillions of microscopic magnetic bits in server farms like this one archive virtually all of the world's accessible digital data. It is a journey that began with a curious rock held in a human hand and ended with engineered quantum states that silently coordinate the global economy. Today, researchers are exploring the use of spin waves and magnons to transmit information through solids without moving the electrons themselves. As we seek to process data with even less energy, magnetism remains at the center of the next major transition in computing.